All right. Recall X-ray tube on the cathode end. We generally have a dual focus system, which means we have two filaments. Remember that? One for large body parts and one for small body parts. The way they're usually set up is like this. These are just examples. Starting with the small, you got 0.5 millimeters, and then you just double it in size. So you got 0.5, 1, 0.6, 1.2, and then 1, 2, and then 2. Anything smaller than 0.3 millimeters or less is known as a microfocus tube. These are probably the smallest type of filaments that you would have to give you the best type of detail. Remember that the smaller the focal spot size, the better the detail. Okay? These are perfect for mammography, angiography, and any other type of procedures where we magnify the image. And we're going to be covering this later on, but anytime you have magnification, okay, so remember this, because we're going to talk about it again later on, but anytime that you blow up an image, when you magnify an image, you are going to lose detail. You are going to lose detail. This may be familiar to you guys already, because when you're taking photos with your phone, okay, and you're cropping it, and you're flipping it, and do all the other stuff to it, what happens when you blow up your image? Have you guys ever magnified the image that you took on your camera? What happens to the image? It gets blurry, and you start seeing the pixelation, all the little dots on your images. Same concept with X-ray, okay? So we'll talk about that later on. But keep this in mind, anything less than 0.3 is known as a microfocus tube. The smaller the focal spot size, the better the detail. Large focal spot sizes are good for imaging larger body parts. The advantage of this as well with larger focal spot sizes is that we can impress more heat on it. But what I mean by impressing more heat is we can jack up the MA. When you jack up the MA, the hotter the filament gets, more electrons are boiled off through the process of what? Thermionic emission. We can't do that with smaller focal spot sizes. Okay, it has a limit. Otherwise, if we get too high with the MA, we're going to burn off those small filament. So this is where the large filament comes in. We can impress higher MAs. The advantages also of having a large focal spot size is, remember the law of reciprocating numbers, law of reciprocity, where we can jack up our MA, and then we can also decrease our time as long as the total mass is the same. You guys remember that concept? So with larger focal spot sizes, we can increase our MA and we can acquire much shorter exposure times. Okay? With smaller focal spot sizes, these are for smaller body parts where detail is of essence. When we're trying to take x-rays of bones, the skull, the hand, the feet, a lot of detail in there where we need a lot of detail. But the problem with that is it's not made for larger body parts. So we cannot impress higher MAs. If we do, we're going to burn out our tube. Okay? Any questions on the small focal spot? All right, let's talk about filtration. Filtration, before we talk about filtration, remember that when the electrons strike the anode, the X-rays that are produced are polyenergetic. Okay? They're not going to be the same energy from X-ray photon to X-ray photon. It's going to be polyenergetic. So what we try to do is, in the path of the X-ray beam, we will place a filter. This is inherent in the tube. The filter, what it does is that it removes any of the softer rays, the softer photon energies, to make the beam more harder, more uniform. It is a term that we use. When you say the beam is a lot harder, that's a term that we use when we're talking about filtration. It makes the beam harder. It's good for the patient because the filter is going to absorb those softer rays before it interacts with the patient. So those soft rays aren't absorbed by the patient. It's going to be absorbed by the filter.
So softer rays are of like lower energy?
Lower energies. Okay. Again, polyenergetic. We're going to be talking about two different types of filtration. The first one is inherent. This is inherent, and what we're talking about here is either the glass or metal envelope of the X-ray tube. The second one here is broken up into two different parts, is the added. The first one here for the added filtration is within the collimator. The collimator simply is what controls the size of the X-ray beam. The beam coming from the X-ray tube comes out wide, divergent, and expanded. We need to control the size of the X-ray beam, especially if we are X-raying smaller body parts. That's what the collimator is. Okay? And then the second one here is placed between the X-ray tube and the collimator box. So between the two, you have 2 added, which is 1 plus 1. So for total added, you're going to have 2. Inherent, you're going to have 0.5. So the total filtration then is going to be 2.5 total filtration. We're talking about 0.5 millimeters of aluminum equivalency. That is the material that we use for filtration. 1 within the collimator box. Another one between the X-ray tube and the collimator box. Okay? So if I were to ask you a question, what is the total inherent filtration? What are you going to tell me?
2.5.
Total inherent filtration.
0.5.
0.5. And when I'm talking about inherent filtration, what am I talking about there specifically? The X-ray tube. Okay. Any questions here? Okay, let's talk about some other types of filtration. This we can also add as part of the total filtration. These are compensating filters. What compensating filters do is that it balances the intensity of the X-ray beam for a more uniform exposure, especially if you're X-raying body parts of different thicknesses or densities. It makes the beam more uniform. We're going to be talking about the wedge and trough filter. These are examples here. You've got the wedge and you've got the trough. With the wedge, it's very similar to that of the aluminum block that I showed you guys a few weeks ago. It goes from very thin to very thick. Okay? We'll talk about the trough here in a moment, but let's talk about the wedge first. Let's just say, for example, we were going to take an X-ray of a foot. The foot has varying thicknesses from the toe to the heel. At the toe is going to be much thinner, towards the heel is going to be much thicker. If we don't control the intensity of the X-ray beam, what's going to happen is that in the areas where it's much thinner, there's going to be more penetration or attenuation at the toes. More penetration, right, because it's thinner. Mm-hmm. And if we make our way down towards the heel, are you going to have more penetration or more attenuation towards the heel?
More attenuation.
More attenuation, so there's going to be more absorption. So what we'll do is we'll place this wedge filter in the path of the X-ray beam so that when we're X-raying the foot, we'll place the thicker side towards the toe and the thinner part towards the heel. All right? So then your resulting radiograph will be that of uniform density. If we did not place a filter in its path, the toes will be dark and the heel will be light. There's going to be varying densities. With the filter, we can make it less intense towards the toes and more intense towards the heel for an even radiographic density. Does that make sense, guys? All right, another example here would be that of the chest. With the chest, bless you.
Thank you.
It's thick down the middle, okay, because you've got your vertebral column, you've got your heart, and you've got your pulmonary arteries here. And in either side of those, you've got an air-filled lung. Is air easily penetrable?
Yes.
Yes or no? Yes, right? So we can just shoot right through air. So without a filter, you're going to end up with a radiograph that's going to be extremely dark. So if we can even out the intensity of the beam by putting a trough filter where it's thicker on either side and thin down the middle where the spinal column is, you will have a radiograph again of even density. The thicker part of the trough filter will be placed over the lungs. The thicker part of the trough filter will be placed down the middle. Okay? So there will be less penetration here and more penetration here. Okay, so those are some examples. We got different types of filters too, but this is just to give you an idea of what we can do to control the intensity of the beam by utilizing filters. So with filters, we can control the intensity of the beam. And if it's added for the primary beam, what it does is that it removes the softer rays, making the beam more uniform. But that's the whole idea of filters, is to make the beam more uniform. Okay, any questions? All right, let's talk about the AltFuel effect. The AltFuel effect is a phenomena in which the intensity of the beam varies from the anode to the cathode end. There are variances in the intensity of the beam from the anode to the cathode end of the X-ray beam. This is due to the way the anode is set up. The anode is set up in an angle. You guys remember my symbol? Every time I draw a symbol of an anode, there's always a slant on the disc. We need a slant to deflect the electron as it interacts with the anode. We need to deflect the X-ray photon towards the patient. That is the reason for the angle. The AltFuel effect comes to play because of the distances the electrons have to travel. Towards the heel of the anode, it is further away. So what happens is the intensity of the electron starts to lose intensity as it's traveling further away. The end result then would be a photon or an X-ray beam with the various intensities. The further the electrons have to travel, the less intense of that X-ray beam being produced. So when you look at the example here, you will see that within the middle you have 100% intensity of the X-ray beam. So if you selected 70 kV, right in the middle of it will be 70 kV. Those that are towards the closer part towards the cathode, the intensity of the beam increases. And then further away towards the heel, the intensity of the beam is going to decrease. All right? But right in the middle, it's going to be 100% intensity. Remember what we said? The X-ray beam is going to be polyenergetic. All right. So keeping this in mind, the intensity of the beam with the AltFuel effect, the intensity of the beam is going to be greater towards the cathode end. So how do we know which is the cathode end? That's pretty simple in the way the room is constructed. The foot end is going to be the cathode end, and the head end of the table is going to be the anode end. So wherever the foot end is of the table, that's going to be your cathode end. All the rooms are built that way. Okay. All right. So then what you understand about the AltFuel effect is that we can take advantage of that by placing, again, body parts of greater thicknesses. Are we going to put it towards the cathode end or towards the anode end?
Cathode end.
Cathode end. So like the foot, we will place the heel towards the cathode end. If I was going to X-ray my hip, okay, my hip from femur, from my knees up to my hip, I will place my hip towards the cathode end and my knees towards the anode end. Is that making sense, guys? So thicker body parts towards the cathode.
Is it the reason that you use the filter?
The filter just makes it a lot better. It's a supplement. It just makes it a lot better.
So it's not because of this force this way?
Right. So we're going to do two. So we're going to use the filter, and we're also going to use the cathode, the AltFuel effect.
So with just proper positioning, would it still not be like? Would it still be darker on both ends, or? without using a filter? Like, say you just position the foot correctly the way it's supposed to be?
No. As long, this right here is where it's called 100% intensity. This is known as the central ray. Actually, good question. Highlight that somewhere. Okay. You can't really mess up in proper positioning because you're always going to place the center of your central ray in the middle of the anatomical structure. So that way you can't mess up. Okay? And the central ray is going to be identified by lights in the crosshair of the X-ray tube, which we'll talk about later on too. Okay? But remember, right in the middle of this, your X-ray beam, right in the middle where you have 100% intensity is known as the central ray. But to answer your question, Bahar, I mean, yeah, you can supplement it. It just makes the image prettier. So you use both the AltFuel Effect as well as compensating filters. All right, so let's talk about generators now. Okay, any questions up until this point? Okay, generators. Some of you guys have already taken 142, electronics and physics. I'm going to keep this as basic as possible for those who haven't had 142 yet. Okay? So what we're going to be talking about are the different types of generators which assist in the powering of our X-ray equipment, which produces X-rays. All right, so we're talking about generators that control the power coming from San Onofre, Southern California Edison, Sempra Energy, whatever. Okay, but we're talking about the electricity that we get. So the radiation quantity and quality produced in the X-ray tube are influenced by the type of high voltage generators that are used. In turn, the technology should also have an understanding of those generators when selecting the proper technical factors. Okay, we're going to be talking about single phase, both half wave and full wave rectification, 3-phase, half wave and full rectification, and lastly we're going to be talking about high frequency. All right, so the first one here is the single phase generators. The electricity that's coming from the electric company is delivered to us in what we call alternating current. You guys all know about AC, right? We receive the energy in alternating current, which means that when we're looking at the energy in a waveform, you have a positive part of the wave and you have a negative part of the wave. Alternating current goes forward and backwards, forwards and backwards, forwards and backwards, but it's forward progression. In a half-wave rectification, because of the alternating current, what we're going to do here is, again, with single-wave, half-wave rectification, we can make use of the positive part of the alternating current. However, we cannot make use of the negative part of the current. So the energy that we're going to produce, or the X-rays that we're going to be producing, is only produced half the time. Okay, remember the energy coming from the power company is alternating current. It's positive and negative, positive and negative. So the current is traveling like this, forward, backward, forward, backward, forward, backward, but it's forward progression. All right, we cannot make use of the negative part of that wave. All right, so again, X-rays is only produced half the time. Now, we're also going to be talking about the rippling effect of this waveform. The rippling effect is talking about, just think about ripples on a wave, ripples on a water. In this waveform, what's going to happen is we will have energy starting from 0, and then we'll peak up to whatever kV we selected, and because of alternating current, it's going to go back down again. All right, until it comes back up, we'll be at 0, peaks up to whatever kV we selected, and then we'll go back to 0. Rippling means starting at 0, peaking up, and going back to 0 again. This is 100% rippling. From 0 to peak, back to 0. It's 100% ripple. Okay. So with single wave half rectification, X-rays are only produced half the time with a 100% rippling effect. For these type of generators, we're going to be utilizing it for like portable X-rays and an X-ray equipment like in the clinics, where we don't X-ray large body parts. It could be the teeth, it can be the fingers, it can be the foot, but nothing too complex or elaborate. Very, very simple type of X-ray procedures. This is where the single phase half wave rectification type of generators come in. All right? What I'm going to do now is I'm going to take it a step further. Let's talk about, on the next slide, we're going to be talking about single phase full rectification. This is just half. Next slide, we're going to be talking about full rectification. Okay, so this is single phase full rectification. Remember on the previous slide, you have the negative part of the wave not being used? Well, with full rectification, we have special tubes within the generator that can make use of the negative part of that wave. So instead of it going negative, we can use these tubes within the generator to make it a positive. Okay? So now what's happening here is that wasted waveform is no longer wasted. We're going to make use of it. So what we've done here is everything that came down here in the bottom has now been flipped up to the top. All this is now up here. We've rectified it. It's been rectified. All right. Now, it is still 100% ripple in that it starts off at 0. We peak 0, we peak 0, we peak 0, and so on and so forth. So you're still getting 100% ripple effect. Okay, and it mimics that of the energy being delivered. So, but it's in forward progression. So the X-ray then is delivered in a pulse. So the X-ray is zzz, but it's so fast you don't hear it, you don't notice it. But the X-ray is delivered in a pulse. Okay. Any question? So everything in the negative part has been used. There is no dead time. But it's delivered in a pulse with 100% rippling effect. All right. Let's talk about three-phase generators. This is just single-phase. Now let's talk about three-phase. Here is your example of a single phase. This is single phase right here. Single. 1. Here's an example of three-phase right here. What's happening here is the energy is delivered in 3 phases, 120th degree from another. Don't need to know that. Just know that the energy is delivered in 3 separate phases. 3 separate phases. All right? So here is one phase we talked about in the previous slide. Then what we're going to do is deliver another energy wave. And then let's do one more. 3 phases. So it looks something like this. You guys follow? So these are for commercially powered, generally driven 3 phases. They're more efficient than the single phase, and there are more X-rays produced for a given mass. Average energy is greater. The X-ray production is near constant rather than pulsed in the previous slide. All right. You still have a 14% rippling effect. You start off at 0. You peak, but before it comes back to 0, another wave comes in. And before that comes back to 0, another wave comes in. But there's still a rippling effect like the waves of the water. But it just never reaches 0. 14%. What we're looking at here is half rectification. So what that means is you still have wasted waves down here at the bottom. These are still wasted. Half rectified. So when you have three-phase half rectification, it's described as 6 pulse. Three-phase 6 pulse. Three-phase 6 pulse. That's describing three-phase generators with half rectification. There are still wasted waveforms in the energy delivered. Okay? Now let's talk about three-phase full rectification. So now what we're going to do here is take these wasted waves and flip them up and put them on the positive part. So all this is going to be flipped up. So if it's full rectification, how many pulses do you think it's going to be?
12.
12. You guys are good. All right. So fully rectified, 12 pulse. Even more effective. It's near constant because look, there's only slight rippling now. It's near constant. So with three-phase full rectification, 12 pulse, the rippling effect is only 4%. It's near constant energy delivered. Any questions? High frequency generators. Here we're looking at near constant potential. Do you see any rippling effect? Okay, it's basically a straight line, less than 1%. So no rippling effect, energy is more constant. These are yours for very sophisticated systems like your CTs, fluoroscopy, equipment used for angiography, mammography, okay? But it is more complex circuitry. It's more advanced, so we're going to be using these generators for more advanced generators and more advanced type of procedures. So your voltage rippling then, we said it was single phase, you have 100% rippling. Three-phase, 6 pulse, 14% ripple. Three-phase, 12%, 12 pulses, 4%. The bottom line is, the less ripple that you have, the less waves that you have, the greater the efficiency of that X-ray generator. And you can also create shorter exposure times, which is great for the patient, right? Excellent for the patient. So the comparison between three-phase and single-phase. Three-phase is more efficient than single-phase. It is going to require more complex circuitry and more expensive to install. But the bottom line is, with the more complex type of generators, it's going to be better for the patient. All right. Let's talk about the other influential factors that influence our technical factors and our selection of our technical factors. So we've already talked about patient thickness. What we're also going to be talking about here is the size and shape of the body, pathology, and also composition of the body part that we're going to x-ray. You have to be very familiar with your patient's body. Okay? We're all built differently. We're not cut out of from cookie cutter. We're all different. There is no one size fits all. What we're going to be talking about here is habitus or body types of individuals. This is your average type right here. It's your stenic patient. With a stenic patient, you have average-sized lungs, you have the correct orientation of the stomach, the bowel is going to form a square shape, your gallbladder should be right in the middle. These are just basics right now. When the patient gets smaller, everything starts to droop and everything starts to sag in the inside. The lungs are going to become longer, the stomach is going to be a little bit more elongated, and the bowels are going to start to sag within your abdominal cavity. And they're going to sag even lower with your astenic type of patient. These are your very skinny, very emaciated type of patients. The lungs are going to be longer, the gallbladder and the stomach and the bowels are going to drop below your hip bones. Okay?